Hello, quick video on eigenvectors and matrices. Quite often, or we might have a matrix like this one here, and we might it'd be useful to know what that transformation is. Alternately, we might have a system, a vibrational mechanical system like the one below here, with some weights and some springs going between them, and we might want to know what the vibrational modes of that system are. And what we're going to use to do this is this set of eigenvectors and eigenvalues, which we do with sort of eigen analysis. So what I'm going to do is pick an example here and work us through it, and also look at a well-known identity, a way of thinking about it. So let's use this matrix here. And what we're going to do through this technique is look for invariant vectors. Yeah, those are vectors that if I put this vector in and multiply it by that matrix, I get some multiple of that vector. Yeah, so if I wrote that in mathematical terms, I take my vector, it called it S, and I multiply it by this matrix here, and I end up with S times some scalar multiple. Now, if that's going to be true, I can rearrange this equation so that I have a matrix here, which is our matrix M minus lambda times the identity matrix, all multiplied by our vector that we're trying to find, must equal the empty vector, like 0, 0, or 0, 0, 0, yeah? Now that's only true, this is only going to be true when the determinant of our new matrix is 0, our composite matrix here is 0, yeah? And that's what we're going to use. We're going to use this to find the answer, and we'll work our way through. So here's our matrix. Therefore, rearranging the equation, our matrix, take away lambda lots of the identity matrix, has the effect of bringing our lambda x and y from over here and moving them inside the matrix there. So rather than having 3, we've got 3 minus lambda in the top left, and the bottom right, again, from where this y comes in here, we have a 3 minus lambda here. And if we calculate the determinant of this matrix, we're just going to multiply those two together, and we're going to take away those two here. So we've got 3 minus lambda squared and minus 1 squared, yeah? So what we're interested in is when that determinant equals 0. So if we set this to 0, we find, look, we've got a quadratic here in lambda. That's because we're in 2D. If we were in a 3D matrix, we'd have a cubic. So rearranging this this equation rather, we've got lambda minus 3 all squared must equal our 1 squared going to the other side is 1, isn't it? And if we root both sides of this, we get lambda minus 3 is plus or minus 1. Therefore, lambda equals 2 or 4. Now, these two values, 2 and 4, we call the eigenvalues. So that's the first part of our analysis. We've found our two eigenvalues. What we need to do now is to find the eigenvectors that pair up with these eigenvalues. Okay, so what we're going to do is substitute those two values back into our equation lambda and see what comes out. So let's have a look. And we effectively do this calculation separately. So look, we've got a left-hand calculation here with lambda. We're going to call lambda 1 our first eigenvector. Lambda 1 equals 2. In our second calculation, lambda 2 will equal 4. Yeah. So if we substitute in place of lambda our value in our equation, we've got 2 here on the left-hand side. So this matrix multiplied by xy must equal 2 lots of xy. If I just look at the top line of this, because in effect what we've done is turn this simultaneous equation into the same equations. Our top line, we'd have 3x plus y equals 2x, yeah, looking along the line here. Therefore, I can write that out. 3x plus 2y plus y equals 2x. If we rearrange that, we find that y equals minus x. So if we wrote that as a matrix using x equals 1, so as a vector, we would see that if x equals 1, y must equal minus 1. So we found our first eigenvector. That's our S1 eigenvector. It's 1 minus 1. And if we go through now on the right hand side, we can do the same calculation for lambda 2 is 4, so I substitute my 4 in there. Looking at my top line again, 3x plus y equals 4x. Yeah, so I've written it there, and a bit of cancelling out here, we find that y equals x. So again, if I write this in vector form, if x equals 1, then y is going to equal 1 as well. So I've got a nice 1, 1 vector there. And these are in pairs, as you can see. Lambda 1, where lambda equals 2, is matched with or paired with S1, the vector 1 minus 1. And on this side, lambda equals 4 is paired with the vector 1, 1. Okay, what's this actually telling us? Well, eigenvector 1 is telling us that in the direction of this vector 1 minus 1, this transformation is, sorry, quick break there. So in the direction of this vector, what this scale factor, that's actually telling us that there's a stretch with scale factor 2 in the direction of this vector. And this matrix also has a second effect, that in the direction of, oops, that should be 1, 1, this second eigenvector is telling us there's a stretch in the direction of this second vector 1, 1, scale factor 4. So what does that mean? Is that helpful in practice? Let's have a look at a diagram, shall we? Because this will take us somewhere. So what it's saying to us is, if I started with this red vector 1, 1, and I multiplied it by, applied the matrix 3, 1, 1, 3, and I just put, if I put 1, sorry, that should be 1 plus 1 there, shouldn't it? 1, 1 there. I would find that I'd get to the point 4, 4. Yeah. So that point here will end up being transformed to 4, 4. Yeah. We happy with that idea? That should really be in red. No, I should have done that in red. So that one's going to 4, 4. And if I had a point here, which is 1 minus 1, and I put it into this vector, I would go from the point 1, 1 to the point 2, 2. Yeah, multiplying that out. So that's quite interesting, isn't it? We've got two separate stretches going on, yeah? What happens if I take a generalized point? Have a look at this. Let's take point P. It's a point here. There we go. There's our point P. Okay, and what we could do is consider P to be made up of two vectors from the eigenvectors. Yeah, so we'd have that bit of the eigenvector of the lambda 4 eigenvector, that's some multiple of 1, the vector 1, 1, and plus this vector here, which is some multiple of the vector 1 minus 1. Yeah. And what the analysis has done, the eigenanalysis has told us, is that for this component, let's do that, the lambda equals 4 vector, the 1, 1 here, if I had that one there as just distance, that whatever that distance is, telling us it's going to be transformed, that part of the vector is going to be transformed to be scaled up, scale factor 4. So 1, 2, 3, 4. So that vector, this part here, would effectively be quadrupled, yeah? And this component, the yellow, the 1 minus 1 eigenvector, which is a scale factor of 2, so if I was at that point there, had this vector component of the P, then I would just double that, so it would go out to this here. And then we'd have to combine them, yeah? Our new position, so therefore we get our new position of the point P gets transformed, yeah? So let's have a look at this diagram. That might be a bit more helpful in this form. So our point P goes to P dash here, and effectively we find the 1, 1 component here, the eigenvector 1, 1, and we go 1, 2, 3, 4 lots of that up to here, and then we add on the 1 minus 1 component, and that got doubled, so 1, 2, so we go up to here. Yeah, so we've gone up all the way along, 1, 2, 3, 4 lots of the first eigenvector component and 2 lots of the second eigenvector component. So can you see that what we're actually looking at here is a way of doing those transformations relatively quickly if we understand what the eigen values are, they give us our scale factors, and the eigenvectors tell us in which directions they're operating. And as you can see here, we've really done something by changing our axes round from our normal ones to these ones at 45 degrees, and we're doing all our calculations in those in the eigenvector axes, in effect, as axes, yeah. Just to bear in mind, those eigenvectors don't have to be perpendicular, but we can still do exactly what we've done here about breaking up a point P into components of the two eigenvectors. Okay, so that was the first thing I wanted to show you. The second part is what that means mathematically, and it fits in with what we've just done. If we took our our original matrix there, we can prove that we can split that matrix. In effect, we'll build that matrix by knowing what our eigenvector matrix, so our eigenvalue matrix is, and an eigenvector matrix is, and then doing this process here, including the inverse, to replace it, to actually generate our matrix. So we could actually start the other way around. We could start with, I want these to be our eigenvectors, these to be my eigenvalues. Tell me what my matrix is going to be. Yeah, that's what I'm going to use it for in a minute. Okay, so in principle, what we know is, from what we've just done, is that by definition, for our first eigenvector and its eigenvalue, we know that's a multiple. If we put that into our multiplied by our matrix, we end up with this relationship. Yeah, our matrix times our eigenvector gives us our eigenvalue times our eigenvector. That's the first one, and it's also true for the second one. So we could combine those into the S1 and S2. So effectively, we've built a little matrix here. Yeah, so there's the first eigenvector, there's the second eigenvector, and that looks like a matrix, and we're going to call that matrix S. So that's our eigenvector matrix. Yeah. So there we go. We're going to call S1, that S1, S2 our eigenvector matrix, which means our left-hand side of this equation just becomes MS. Yeah, we take our M matrix and we multiply it by our eigenvector matrix, and we get another matrix. On the right-hand side, it's not so obvious, but here in the first part of our matrix, the left-hand effectively parts of it, we just have lambda 1 times our S1 eigenvector, and in the other one that should be lambda 2. In the second row set of columns, second column, or we would have our lambda 2 times our S2 terms. Now, we can do that mathematically, and if I did a bit more work, I could show you that in effect what we got there is we take our eigenvector matrix and we multiply it by an eigenvalue matrix, which is going to look like this. So effectively it looks like the identity matrix, doesn't it? But on the leading diagonal we've got our lambda 1, lambda 2. Now if we accept this line here as being true, by definition, then there it is there, and that's it there. Then using matrix multiplication, if we post multiply by matrix, the inverse matrix, S minus 1 to both sides, then our left-hand side is just going to simplify to M, and our right-hand side is going to have this S eigenvector matrix times the eigenvalue matrix times the inverse of the eigenvector matrix. That's just going to work like that. So there's an identity. So let's use our example, shall we, to work our way through this and what it means in practice. Okay, so here's our matrix, and what we're going to do is create two matrices here, one of which is going to be our eigenvector matrix, and in the first column of it, it's going to have our first eigenvector x and y values. In the second column, it's going to have our second eigenvector column values. In this case, I've done the first column as being the 1 minus 1 vector, and that was matched to an eigenvalue of 2, wasn't it? So in the first column of our eigenvalue matrix is going to be R2 on the leading diagonal, and all the other terms are 0. That's the whole point of doing this, is we've effectively created a diagonal matrix. So that's going to be our S1 and our lambda 1 column, And in the second column here, we've got our second eigenvector, which was 1, 1, and that had a scale factor of 4, an eigenvector of 4. Yeah. So here are my two matrices that I know from my analysis make up that matrix there. Yeah. Then if I go through and do the calculation here, m equals s lambda s minus 1. I need s minus 1. Well, I can find out, find the inverse of s, can't I? By doing ABCD becomes dA minus B minus C, and then the determinant's out the front, and we get this matrix here. It's a bit like the original, doesn't it? But it's got half out the front. And then if I just put those matrices in, here's my S matrix, there's my lambda matrix, there's my S minus 1 matrix. If I multiply these first two together, I get this matrix here. That's my S lambda combined matrix. And there's my S minus 1. If I multiply those through again, I'm just rearranging, sorry, to bring the half out the front, because we can move that anywhere, unlike the matrices themselves. If I multiply those two matrices together, I end up with this 6, 2, 2, 6 matrix, and I've got half out the front, and therefore it simplifies to our matrix M is 3, 1, 1, 3. So what we can do, as I say, is using this sort of approach, we can actually start off with the eigenvectors that we want and the eigenvalues that we want and create a matrix that achieves that transformation. That transformation could be a stretch, it could be a reflection, depending on our values of our eigenvalues. If we use complex eigenvalues, we can actually do rotations. So finally, here we are. A quick summary of what we've done. Eigenvectors rely on finding invariant eigenvectors. So they satisfy this equation here. Therefore, the determinant of our combined matrix must be 0. So that's going to give us a quadratic or cubic in lambda to solve. Once we've got that, we get a pair. We get an eigenvector and an eigenvalue in pairs. And if we've got a 2 by 2 matrix, we have two eigenvalues. We have two pairs of eigenvalues and vectors. If we're doing a 3 by 3, we'll have three eigenvalues and vector pairs. Okay, and we can work the other way round from our eigenvector matrix and our eigenvalue matrix to actually create a combined matrix if we wanted to do that. Bit of a long video, but I think that's well worth doing. I hope that's of use.